Hello, my name is Konstantin Khabarlak, and this is my plenary presentation for strain adaptive MobileNet for fast anti-spoofing. First, what is anti-spoofing? Anti-spoofing is a special type of a classification problem where the task is to say whether this is a real photo, what we understand when we say real photo. Real photo is when you take your phone and just photograph someone else. This is real, or also known as live photo. However, if you take a picture of some printed photograph or maybe of a computer screen, this will be spoofed or fake face because this is not an alive face. Why this problem is at all important? Because these days we use our face for many tasks where we need to authenticate ourselves. It might be your smartphone, it might be some payment system, or it might be access control system to some kind of enterprise, lyceum, university, and so on and so forth. If we can just present our photograph instead of some person, then this system will not work. This system will not be efficient at all. If it can be tricked just by a picture, it is inefficient. Most systems that do not implement anti-spoofing will be tricked by a photograph, which makes them almost useless. So if we implement anti-spoofing algorithm, and if it is reliable enough, we will be able to say that this is a real photograph, and this photograph can go to further stages of face access control or other face authentication system. But if it is a fake face, it will be rejected at once, momentarily, and this person with this photograph will not be allowed to come in. Which types of image spoofing do we know? Well, first and the easiest one is printed. We can print a photograph, a poster, or just on an A4 piece of paper and present it to a smartphone. Next is a paper cut, somewhat more complicated problem, where we not only print some face, but we also cut it so that it can be overlaid onto someone else's face. Next is replay attack. This is a photograph or a video of some other person on a smartphone, PC, or a tablet. And the final category presented. So this is categories that are presented in syllabus spoof dataset. The final one is 3D mask. It is actually very similar to paper cut. In this case, the authors of this dataset just tried to hold the paper cut so that it resembles a 3D face, so that it is not flat but in a 3D shape. Okay, so it's a classification problem, and convolutional neural networks are very good at classifying images. So a brief recap of key layers of a convolutional neural network. The first one is a convolution. This is a type of filter that is applied at each patch of an image one by one. So we apply it, for example, in here, then we move this filter a little bit and apply it in here, and so on and so forth. This is the key operation that is used to extract features from an image. Next operation is max pooling or just pooling. This is the operation that tries to reduce the size of features so that it becomes easier to process. We also have activation functions. ReLU is the most typical activation function. And we have dense final layer that will be used to output classification probabilities for each class. This is the basic neural network we are all used to see. However, it is very simple and sometimes inefficient, especially if we want to build very deep convolutional neural networks. In those cases, we want residual blocks. What is a residual block? It is a block when there are several convolutions and activation functions, one after another. But take a look. There is another branch that goes around those activations and passes input intact to the output. And then processed features by the two convolutions are added element-wise with this intact signal. Why do we want to do this? Because it significantly improves gradient propagation. Typically, if you try to build a very deep convolutional neural network that has no residual or skip connections, at some point, if it becomes very deep, it will be very inefficient to train. It will be very slow to train, and the final result will be quite poor. However, if you add this connection, it will be much better. This type of connection was presented in ResNet architecture and the corresponding paper. The next one, a bit more complicated, was presented in MobileNet v2 paper, and it is called inverted residual block. It has 3 blocks in a row. We will discuss them in detail a bit more further, and it also has skip connection. How these 2 blocks are different? Inverted residual block is generally more efficient. What do I mean? It gives a reasonable quality at a lower computation cost. So we have discussed basic approaches how classification problem can be solved with convolutional neural networks. But is there something more specific to anti-spoofing? Yes. So here I present several of the recent anti-spoofing methods that use typical backbones for classification, and then they change something. The first one is about central difference convolutions. This work is from 2020, and it replaces usual convolutions with central difference. Central difference convolution computes the large shown in yellow in here convolution as usual, and then subtracts central part of it. Why do we want to do this? Because we want to estimate how color changes in a JSON pixels. It turns out that color change is very important for anti-spoofing problem solution. Another way to solve this problem is IENet neural network. It is also from 2020, and it is also a neural network that was presented jointly with Cele-based spoof dataset. In this work, we also use Cele-based spoof dataset to train and to evaluate our method. So we have an input image and then a convolutional neural network. This network takes multitask approach and tries to predict face features, also reflection and illumination maps. It turns out that reflection and possibly illumination are significantly different if you take a spoofed photograph versus a real one. Why is that? Well, because if you take a picture of a real human, our skin is not as reflective as a photograph or smartphone or your PC. Those screens will be much more reflective, and if we try to predict reflection map, we can more easily understand whether this is a real or spoofed image. In this illustration, you can see that this image is spoofed and reflection map is very very clearly seen. And this one is real, and there was almost no predictions, or almost no reflections predicted. And obviously the key prediction is whether this image is spoofed or live. What do we present in our work? We present post-trained adaptive neural networks. What is it and which kind of problem does it solve? So most of these approaches are very computationally intensive. They have a lot of extra computations which makes them hard to apply on a budget, let's say, on a PC that has not very good performance, or even on your smartphone. Their applicability there is poor. Also, if we take, for example, one of the backbones from this previous slide, like ResNet or MobileNet v2, the problem is that we want to apply this neural network on many devices. Maybe those will be budget smartphones, low-end smartphones, and also high-end smartphones. Maybe we will want to apply them on a personal computer. Those performance tiers are significantly different. So what is the solution at this point in time? Well, we can train a single neural network for all these devices. But on some devices it will be, well, fast enough, just right. On some devices it will be slow, and on others it will be so fast that there will be enough room for something else to be processed. So we will be underutilizing our computer. Why is it important? Because maybe if you can build a more advanced neural network, you can get higher accuracy. Maybe we just want separate networks for each device so that the accuracy in this very important problem is at maximum. But in the modern day, most neural networks will require you to configure each network and then to train it. So we will have multiple trainings for each type of neural network. This is problematic because it takes time and effort. What do we propose in here? A neural network that can be trained just once, and then it can be configured for the target device. How do we achieve that target? We present a post-train adaptive block. Post-train adaptive block has 3 inverted residual blocks and is a drop-in replacement for a pair to inverted residual blocks found in MobileNet. So inverted residual block has 3 operations. First is a one-by-one convolution followed by normalization, batch normalization, and Relay 6 activation. This layer will expand the number of channels. The next one is 3x3 depthwise convolution followed by normalization and activation. It will process that input with an extended number of channels. Next, we also have one-by-one convolution followed by batch normalization with no activation function. This layer will reduce the number of layers that was expanded in this first set of layers. And also we have skip connection in here. So we will take 2 blocks and put them one after another, and we will put 1 block to the side. And then we have an adaptive selector in here, and we will infer either this branch on the left or this branch on the right. And we will call that branch on the left is light. This is light branch, and this branch on the left that contains 2 residual blocks will be heavy. This is a heavy branch. We can also possibly infer both branches. And if this is the case, we will denote such case with letter B. What does it give? It gives us a possibility to configure this neural network after being trained, theoretically. But there is a problem. It is unclear how to train this type of neural network. We will discuss this. Just think of it. Any ideas how it can be trained? But we will take, at this point in time, we will take a look at the modified configuration of MobileNet with PTA blocks. As you can see in here, in 3 occasions, inverted residual blocks were replaced with PTA blocks. Here, here, and in here. Actually, pairs, 2 inverted residual blocks, one by one, were replaced with a single post-train adaptive block. So training. First, it is very similar to training of a common neural network. We have a loss function, cross-entropy loss function in here, and we have gradient methods used with alpha learning rate of 10 to the minus 4, 20 epochs. Best model is selected on validation and results are shown on a separate test set. Syllabus spoof dataset has separate train and test sets, and validation is created by us by splitting train set in proportion 8 to 2. 2 is for validation. So how do we train post-train adaptive block? In contrast to conventional neural network, once again, MobileNet with PTA is trained just once. To train all types of configurations, we sample different block configurations during training. In the table on the right, you can see configurations. If you might recall, we have 3 PTA blocks, and each of them can be in one of 3 states: heavy, light, or both. Note that we never use both configuration. Never 2 ways, light and heavy, are executed at once during training. This will have some consequences in future. We will discuss them. Heavy is sampled most of the time, and other configurations are sampled less frequently. The logic is that the lighter the configuration, the less frequently it should be sampled. So anti-spoofing, this is the image that we have discussed of spoofing types. What are the key metrics? The first one is attack presentation classification error rate. It is a proportion of attack images incorrectly classified as normal images. It will be shown as upser in the following slides. Bona fide presentation classification error rate, a proportion of normal images incorrectly classified as attack images. And finally, ACER, average classification error rate, is just an average of those 2 values. Note that all these 3 values are error rates, hence the lower the better. Also, we will have accuracy, the higher the better. So we have no PTA configuration. This is just plain MobileNet v2, and we have different types of configurations for MobileNet v2. Note that this is a single neural network. It was trained once, and after being trained, we can select which type of configuration should be used. As you can see, let me just emphasize this first. No PTA and PTA heavy is equivalent in the number of parameters. They're absolutely equivalent in activation functions and everything else. Still, you can see that it is better than no PTA in every aspect. Maybe in some aspects it's like in Bipser slightly better, in other it's more significantly better, but it is always better, despite the different training scheme, and actually thanks to different training scheme and block sampling, it is better than no PTA configuration. In this table and in all tables, in all following tables, red is the best result and blue is the second best. Also, the lightest configuration turns out to be quite good. Accuracy and Bipser are the best with the lightest configuration. And also note that both configuration that was never used during training is the best in average error rate. It is the best in Acer, while it was never sampled during training. Also, we have a comparison of inference time. We have a number of parameters in the network, estimated number of multiply and addition operations, inference time on Snapdragon 845 and Snapdragon 800 devices. Those are to smartphones. PTA networks are easily applicable to smartphones and are very efficient for smartphones, but they can also be used for just your execution on server or on a PC. Obviously, PTA light is the fastest in here. Performance improvement is around 20%. PTA HHH is equal in inference time and number of parameters with no PTA, obviously, and other configurations are somewhere in between. Also, both configuration is only 7% heavier in inference time than no PTA configuration. And while this is faster, all these configurations are faster, they're also more accurate and have lower error rate. Also, training. Training is very important. If the network is trained twice as slow, it takes twice more time to train the network, then maybe it's not so great neural network. But our PTA-based neural network is actually 15% faster to train, while still achieving, as I said, better accuracy and lower error rate. In here you can see the exact numbers. Also, we have plotted Acer average error rate throughout training as measured on validation set. And it is always better. This orange dashed line is for MobileNet with PTA blocks. It is always lower and better than just pure MobileNet v2. And it is much faster to train at initial stages. So demo time, here is the demonstration of it working on a mobile device. So I run it in real time on my smartphone, and I presented another smartphone, recording of me taken on another smartphone, and it is properly detected Anti-Spoofing. If I take a picture of my face or just show my face, it will say that no spoofing is detected. So, summary. In this work, we have introduced post-train adaptive neural network. Crucially, it is trained once and can be reconfigured later to suit your performance needs. The lightest configuration is 20% faster and has higher quality, just as all configurations are better than no PTA. The PTA BBB with both branches in all three PTA blocks has 23.5 relative improvements in Acer over baseline, and this network is also 13% faster to train. This is the final slide where you can see some useful references. On the top is this work, post-train adaptive MobileNet for fast anti-spoofing. And also you can find several of the previous works on a similar topic that you might also find interesting and useful. For details on references, you can take a look in video descriptions. Thank you.